Okay, let's jump right into this explainer and tackle a truly fascinating and honestly kind of apocalyptic scenario that totally flips what we thought we knew about the air we breathe. I mean, we all grew up learning that trees and plants are the lungs of the earth, right? That without them, we'd literally suffocate. But what if I told you that from a massive planetary perspective, that's not exactly how our atmosphere works? Today, we're breaking down some incredible math and digging into a landmark 1974 geological paper to uncover what is actually keeping our planet. To kick things off, I want to hook you right away with a crazy, visceral question that popped up on a popular online math forum. The question was this: if all plants disappeared today, how long would it take for the atmosphere to become completely unbreathable? It's the ultimate myth versus reality journey, you know? Your gut instinct probably says, well, we'd have maybe a few days or a couple of weeks at most before we're all just gasping for air. But the people who actually sat down and crunched the numbers, they revealed something entirely counterintuitive. Let's actually look at the math here. You've got this colossal number, 1.4 times 10 to the 18th power kilograms. That is the total mass of molecular oxygen currently floating around in our atmosphere. It is, frankly, an unfathomably massive reserve. Like, yes, of course, plants and bacteria are constantly cycling oxygen in and out, but the sheer volume of our atmospheric bank account, so to speak, is just absolutely gigantic. And because of that massive buffer, researchers calculated a mind-blowing reality. If just the plants vanished today, meaning absolutely no new oxygen was being pumped into the sky by forests or algae or anything, it wouldn't take days to run out. It would take over 10 millennia. You heard that right, 10,370 years for the oxygen to reach absolute zero. No way, right? But okay, human biology is a little more fragile than waiting for absolute zero, which brings us to a rather grim but super fascinating timeline. Let's walk through this hypothetical timeline of human degradation. Let's say at year zero, all photosynthesis just stops. Boom, gone. By year 330, the oxygen concentration in the air drops from our very comfortable 21% down to about 19.5%. And that's the threshold where humans would definitely start feeling some serious negative physiological effects. Jump ahead a bit more to year 1330, and oxygen drops below 15%, which is a level where human survival wouldn't really be feasible anymore. But here's the deeply ironic truth you should take away from all this. Long before we ever reached year 330, the entire global food chain would have completely collapsed. I mean, we would all literally starve to death centuries before we ever actually suffocated. And this brilliantly illustrates our pivot for this explainer. If plants aren't actually maintaining our immediate moment-to-moment survival from an oxygen standpoint, then what on earth is controlling the air over the long haul? Well, to answer that, we have to turn to this abstract from James C.J. Walker's phenomenal 1974 scientific paper, Stability of Atmospheric Oxygen. See, Walker realized that the fossil record shows our atmospheric oxygen has remained incredibly stable for millions and millions of years. Something way, way bigger than trees has to be acting as a global thermostat. To really understand this, we need to define a crucial term: the geochemical budget. Basically, this is the combined set of planetary processes that separate oxygen from its compounds, produce it, consume it, and bury reducing materials. So we're zooming way out here. We're zooming out from the human scale, and even out from the biological scale, to a massive, massive planetary scale. We are talking about the chemistry of the Earth's crust itself. You can think of it as a tale of two completely different cycles. On one side, we have what's called the fast cycle. This is the biosphere. It's plants photosynthesizing, animals breathing, things dying, and things decaying. It's fast, it happens over days or maybe decades, but it's basically a closed loop. Plants make oxygen, and then decay eats that exact same amount of oxygen right back up. But on the other side, we have the slow cycle, and this happens deep, deep in the earth over millions of years, driven by the burial of carbon and the slow weathering of ancient rocks. Notice Walker's really complex flow diagram of these exact cycles. The tiny reservoir representing the biosphere is completely dwarfed by the massive atmosphere reservoir above it and the absolutely gigantic sedimentary rocks reservoir below it. Walker points out that the biological cycle is essentially just running in circles. For the atmosphere's oxygen level to actually change in any meaningful way, it relies on this incredibly slow, deep Earth machinery. So, how exactly does this slow machinery work? It's like a giant puzzle. Step 1, photosynthesis produces carbon and oxygen. Okay, normal enough. But step 2, and this is the absolute magic part, a very small fraction of that organic carbon doesn't actually decay. Instead, it gets buried in sediment. And because it's safely buried, step 3 kicks in. The oxygen that would have been used up to decay that carbon is just left behind in the atmosphere. It's a net gain. But to balance that all out, we have step 4. The weathering and erosion of old rocks acts like a giant sponge, eventually consuming that leftover oxygen over millions of years. So the tiny net source of our breathable air actually comes from the fossilization of carbon, not just your everyday plant life. This right here really builds Walker's core theory. The rate of oxygen consumption via weathering acts as a massive sink. I want you to imagine huge mountains slowly eroding over millennia. The minerals exposed by this erosion literally react with the oxygen in the air. They oxidize, or, they basically rust, which essentially consumes oxygen. This continuous process proves that the weathering of old rocks acts as this massive sink, constantly pulling oxygen right out of the sky. So the crucial takeaway here is that this deep Earth thermostat depends entirely on specific geological factors. Things like the rate at which tectonic plates push up mountains, or the erosion rates carrying material down to the sea, the amount of carbon packed inside those eroded rocks, and how much of it actually gets oxidized. These are massive planetary gears, and they operate completely independent of, how many trees happen to be currently growing in your neighborhood. Okay, so if weathering is the sink that's destroying oxygen, where is the ultimate source that's producing it? Well, looking at the Pacific Ocean, those shaded areas represent ocean margins and nearshore deposits. This is exactly where immense amounts of sediment are being dumped into the ocean. These deep, rapid burial sites are where organic carbon is hidden away from oxygen. And this burial prevents the carbon from decaying, permanently leaving its corresponding oxygen completely free to hang out in the atmosphere. And here is where Walker's genius really shines through. He proposes this completely brilliant negative feedback loop to explain why oxygen levels never just spiral out of control. Imagine oxygen levels in the air start to drop for some reason. What happens? Well, the deep oceans become more anaerobic. They literally lose their dissolved oxygen. And because there's no oxygen down there to rot the dead material falling to the sea floor, way more carbon gets safely buried in the mud. And because more carbon is buried without decaying, more freshly minted oxygen is released and left behind in the atmosphere. It perfectly stabilizes the planet. It's a real game changer when you think about it. It's basically a self-correcting planetary machine. Now, to truly appreciate the sheer scale of this geological lung, let's transition back to the incredible math from our online researchers with a quick, engaging setup. If the atmosphere is just a tiny waiting room for oxygen moving between rocks and mud, where is Earth's oxygen actually hiding right now? Prepare to have your mind blown by this massive disparity. Roughly 99.5% of all the oxygen on planet Earth is permanently locked away in the crust, in the form of rocks and minerals right beneath our feet. The atmosphere we breathe, the mighty oceans, and literally every single living plant and animal in the entire biosphere combined, they account for less than 0.05% of Earth's oxygen. We're just a tiny, tiny sliver of the actual oxygen cycle. To tie this entire explainer together, let's look at this incredibly elegant quote directly from Walker's 1974 paper. He wrote, "We may conclude that the oxygen crisis that would result from the cessation of photosynthesis would, from man's point of view, occur in the very remote future." He proved, decades ago, that the whole myth of instant suffocation is geochemically false. The Earth's deep, rocky machinery is just way too vast and incredibly patient to let us run out of air overnight. So I'm going to leave you with this final, provocative thought to ponder. When you step outside tomorrow and take a deep, deep breath of fresh air, are you really just inhaling the exhalations of plants? Or are we all just taking a tiny breath inside Earth's massive, multi-million-year geological lung? The next time you look at a mountain, remember, it's doing just as much breathing as the forest at its base. Thank you for joining me for this explainer. Keep questioning what you think you know and keep learning.